In subtopic 7.1 we looked at the atom as a whole. In 7.2 we then sort of focused more in on the nucleus itself. In this subtopic 7.3, the structure of matter, we're going to go even further again and look at what's inside the nucleus in other subatomic particles. In order to do that though, we first need to just touch on some models of the atom. Now my preference here would be to actually go through these models in much more detail, but the IB syllabus doesn't actually require that, so we'll just briefly touch on them so that we've got a bit of an understanding of where we've come from and where we're going to, I suppose. So the first thing that to identify is that our understanding of what makes up matter has developed quite significantly from what the original thinking was way back in ancient Greek times through to what we currently know and where we're sort of looking further ahead. So our understanding has developed quite significantly throughout history. So I'll just jot down a couple of the key scientists in particular and identify some of the models that they proposed. Again, as I said, not going into much detail, but just to give you a bit of an overview. It's an interesting progression if you look into it in more detail and look into the experiments that were conducted in order to find out more about the atom itself. So first of all, if we start off with the ancient Greeks, the common understanding back then was that all matter was made up of 4 elements, and those elements being fire, air, water and earth. Now it might sort of seem a bit strange to think that that everything could be made up of just those 4 things, but if you sort of think about it, you start to combine some things. So if you combine water and earth, for example, you'd end up with mud. If you combine, say, air and water, you end up with bubbles. So you get these different substances that you can sort of see how they might have understood that they were the things that made up all of the matter that we saw around us. Just as a side note here too, though, there was a philosopher whose name was Democritus. He actually sort of thought a little bit more carefully about matter and sort of thought, well, if I take a lump of clay and cut it in half, then I'll have 2 smaller lumps of clay. If I keep cutting those lumps smaller and smaller, eventually I've got to get down to something that is that can't be broken down into any smaller parts. And so he came up with this idea of atomos. You can see that that's where we get the name atom. So he proposed that there were these things that were small indivisible particles. So that was way back in ancient Greek times, but it wasn't an idea that really took off because he couldn't provide any evidence behind it, and as a result that idea sort of sat dormant for a number of centuries until we come to the next significant step. So the scientist that we're looking at here is Dalton. Now we're talking here in sort of the late 1700s. So as I said, just a few centuries, quite a number of centuries past the ancient Greeks, where Dalton proposed a billiard ball model. So if you think about this idea of atoms being small indivisible particles, he proposed that these particles could be considered to sort of be billiard balls that would bounce off each other. They might join together here and there, but basically we've got this idea of this particle that sort of is basically just a small sphere. The next person then is J.J. Thomson, and his contribution starts to introduce charge. The model there is known as the plum pudding model. Now the important thing about his model is that in some of the experiments that were conducted, he identified that we had these charged particles that were being given off by atoms of gas. And so if they're being given off, they must come from the gas somewhere, and from the particles that make up the gas. And so he was actually largely responsible for introducing the concept of charge into atomic structure. So by starting to identify that there's charged particles in the atom, we can start to see that we've got a better understanding of some of the phenomena that might be observed in experiments. Now, it's called the plum pudding model because he basically proposed that the atom is kind of like a plum pudding, where the plums that are in the pudding would represent the electrons, and the rest of the pudding would be just sort of charged, positively charged mass that the negatively charged electrons existed in. That then leads into the next one that we need to spend a little bit of time on. So this one's actually identified in the syllabus that we need to make sure that we've got a reasonable understanding of. And the scientist here is Rutherford, who's actually a New Zealander. And this dates back only to the early 1900s. And it's known as Rutherford's alpha scattering experiment. I'll just mention here as well that it's kind of interesting that Rutherford didn't actually conduct the experiment himself. He was supervising two of his students that were conducting it and made some suggestions, and that ultimately led to the conclusions that he was able to draw. Now, in order to explain this, I'm going to draw a diagram. We'll start off with this sort of cross-section of what's basically just a whole series of atoms of gold. So this here is a representation of a gold foil that's only a few atoms thick. So it was critical that we had a fairly thin substance, so that the in dealing with the alpha particles, we could actually make see what we be able to make conclusions from the experiment itself. Now, I'm going to represent in, or keep it in blue, what the expectation was here. So we have on the left hand side some alpha particles. Now, at the time, they obviously didn't know about the structure of the atom, and so these alpha particles were just particles that were given off during radioactive decay. We know now that those alpha particles are actually a helium nucleus, but the important point to note is that they are charged particles, and they are positively charged. Now, the idea was to fire those at this gold foil and see what happens. Now, the expectation, based on the fact that at the time the hypothesis, or the understanding of the atom was Thomson's plum pudding model, the hypothesis was that most of these should just pass straight through. So that was the expectation, because if you consider these the plum pudding model, the charge fairly evenly distributed throughout the atom. So the hypothesis is that those effects of the charge in the atom should basically cancel out, and that most alpha particles, or all of the alpha particles I should say, all of them will pass through undeflected. So no real effect. The particles aren't going to experience any change, and they'll just continue straight through as if the thin gold foil wasn't even really there. Now, when Rutherford's students conducted this experiment, they did actually find that most particles passed through. So I'll change colour now to represent the observation. So I'll just make a note there. The colour that we're using here, the lighter blue, is what the observed results were. So most did pass through undeflected. So they saw what they very much expected to see, but in order to confirm that that was the case, they obviously couldn't just measure the ones that were passing through. They had to measure sort of out to the side a bit as well. And what they started to observe was that while you did have a lot of these ones that were just passing straight through, every so often there would be one that would sort of travel through, and then it would be deflected a small angle. So they observed that some were deflected up to 90 degrees. And at Rutherford's suggestion, they actually measured around the other side as well, and they found something even more strange. So they'd found that some of these particles, as they were travelling through, would actually be deflected more than 90 degrees. And weren't many of them, but there were some. So we're talking one in about 6,000 were deflected more than 90 degrees. So to put that into context, Rutherford himself said that it was quite surprising, and he's quoted to say that it would be like firing a 15-inch shell at tissue paper and having it come back to hit you. So imagine like something coming out of a cannon being fired at a piece of tissue paper, and then that bouncing back off the tissue paper to come and hit you. There's no way that you'd expect that to happen in that sort of scenario. So that then allowed some fairly important conclusions to be drawn, and this is the really important aspect of this experiment, are these conclusions. So two things that we can conclude there. The first is that most of the atom is empty space, and that empty space is where the electrons orbit. So we've moved away now from electrons being evenly distributed through a plum pudding model to electrons orbiting, and the thing that they're orbiting is where most of the mass and where the positive charge is concentrated. And that's concentrated in the center of the atom, and as we now know, that part of the atom we now call the nucleus. So this experiment was really where the nucleus was first discovered, and allowed a lot more discovery to happen after that. I'll just mention here too that if you consider the distances that we're talking about here, the atom size, or the atom diameter in this case, we're really talking in the vicinity of, say, 10 to the -10 meters. Now, it seems like a fairly small distance, and in fact it is, but compared to the nucleus diameter, it's really quite large. So the nuclear diameter is in the order of 10 to the -15. Now, really want to draw your attention here to the fact that that measurement there is a factor of 100,000 times larger. So the nucleus, imagine the size of the nucleus, and then go 100,000 times larger is the size of the atom itself. So quite a large difference between those two. So the last point to note here, so that we can move onwards through our this subtopic 7.3, further experiments then allowed by other scientists. Further experiments by other scientists showed that there was even more to understand about the atom. And keep in mind that we're now really only talking about the last 100 years or so in terms of scientific discovery of the atom and of the nucleus, and of things that are even smaller than protons and neutrons. So it's not just we don't arrive at our understanding just by happenstance. We have arrived here because numerous scientists have discovered certain aspects about matter and the atom and what they're actually made of. To put it into context, by the end of the 1960s, there were over 300 subatomic particles that had been discovered. So no longer are we just talking about protons, neutrons and electrons. We're talking about quite a lot more than that makes up all of the matter that we see around us. And that discovery of all of those particles led to a classification system, and that's what we'll spend most of the rest of this unit on, that's known as the Standard Model. Now, a bit of a heads up here that the Standard Model and some of the particles that we're going to be looking at are a bit strange. It's a bit weird, it's a bit abstract, so it might take a little bit to wrap your mind around it. In most cases, it's literally just a case of taking it on face value and making sure that you can state the properties, state the differences between certain particles, and be able to use the classification system to distinguish between certain scenarios. So that's what waits us in the next video.